Hello, how are you? Fine? Are you
Fine,
okay in
thank
the
you.
room? Okay, we start this roundtable about quantum for finance review of use cases in finance. I think you have a really interesting use cases to talk today. First, Ali, how long has Crédit Agricole been interested in quantum? How did this come about? How can you talk about this story and how you start to work on that?
Sure. Is it okay? Okay. Thank you, Fanny, for this invitation to talk about the quantum computing initiative within Crédit Agricole CIB, which is now more larger than CIB, as Eric just presented. Actually, we started a couple of years ago, around 2019, with a few of our collaborators interested by themselves in this fascinating field, actually. Actually, we have within investment banking a lot of scientists, engineers, etc. So it was natural to look at this field. Also with regards to the fact that we use intensive calculation within finance for risk management calculations, for pricing of financial instruments, etc. So when you use grid computing, you use GPUs to accelerate the calculation, to calculate measures more accurately. So it's natural to look at the innovations, and we heard about quantum computing in the press, in the media, and it was natural to try to look in depth to this field and start trying to understand this complex technology. So we formed a group of early interested collaborators, and we went to meet some of the actors of the ecosystem, be it industrials, consulting firms, academia, etc., in order to understand more about it and more about the promise and the reality of the promise for finance. Until the day we met our executive committee to talk about this upcoming revolution. And the question was not if this is gonna change the finance industry, but when. We quickly arrived to this conclusion because, as Eric Kahn said, the big companies should not only look at the probability of occurrence of disruption, but also at the severity. So even though we can discuss the probability of occurrence of a disruption, we need to look at the severity, and the severity in case of occurrence of a quantum computer industrialized in the financial industry is going to be massively impacting the way we work today. So this was our rationale, and the executive committee was convinced by our rationale and encouraged us to develop a roadmap to implement. Starting from a question of what Crédit Agricole CIB should do in order to be in position to use accurately a quantum computer, let's say in 2030. And so this is the part of the story that I call the bottom-up part, and there was also a top-down part of the story. That started by a presentation from Quantonation of quantum computing to the executive committee of Crédit Agricole SA. So Philippe Brassac, who is interested by himself in quantum computing, was really very interested, as I say, and passionate about it, and invited the Quantonation to do this presentation. And then we, closed the dots between and the gap between the field, the early adopters from the field, and the exec committee. And in 2021, early 2021, we started talking with Pascal and Multiverse about what can we do together in order to realize this, or start realizing this promise of quantum computing for finance.
Thank you. George, when you start to build your computer, do you think already about use cases, or you adapt during the construction of this computer to be more performant for the use cases?
Absolutely, and it's even more than that. I think it has been a trigger for the creation of the company, at least for me. I know you cannot develop a technology and turn it into a product if you don't have any customers and if you don't have applications. So it was really important for me to have some applications in the short term when we created the company. And 4 years ago, it was still a bet, you know? I mean, to believe that we could do something useful to the market with the current technology. Because, you know, we had only a couple of quantum algorithms at that time, and they all request a lot more of, let's say, of performances on the hardware. But with my co-founders, we had this feeling that we could do something with the current technology. And now, with the work with Multiverse and Crédit Agricole, finally, we proved that we were right. We can do something with the existing technology, mitigating the errors, and introducing new approach for programming the quantum processor. So yes, we think of applications from the start, and it is still a very strong effort in the company to identify the kind of application we can tackle. As Ali mentioned, we are still in a bottom-up approach. Regarding your last part of the question, the beauty of our technology at Pascal is that we do not need to change the hardware to tackle a new use case. Actually, the technology is very flexible, and we can reprogram it at will to adapt to adapt the processor to the use case. But this is programmable, and it can be changed from shot to shot. And that's the way, actually, that we are mitigating these errors, you know, with this capability of controlling the processor at a very low level.
Thank you. Michel, we don't have the power of the quantum computers, the promises of the speed. When you work on software, actually, how it works, when you start to develop this software, what is your way to do on this use case?
The question is also regarding why to do software when hardware is not yet ready. Is that?
Yes.
I think it's worth doing a little classification exercise. If you can take 2 minutes for that, and for audience as well. You know that quantum computing is made of several paradigms, more or less mature. So we have the quantum annealers. I will start with non-quantum machine. I will start with classical machine, with quantum emulators. You know, quantum emulators are running on classical computers, and they are specifically designed to mimic the behavior of a real quantum computers, but they have still some limitation in terms of size of the algorithm. This type of tool is very good for, and is in perfect introduction to quantum computer programming. In fact, I think the best known emulation tools is from the company Eviden, Exatos, and the name of this platform is Quantum Learning Machine. We have now quantum annealers and quantum analog simulators that use quantum effect to solve optimization problems or to simulate complex quantum interaction. In this category, Pascal computer is one of the well-known, best-known, and we know that in the realm of quantum computing, quantum annealer and quantum simulator are two types of computers that are more mature than others, clearly, and we are close to surpass the performance of traditional computing in certain specific case, as demonstrated with the CASI project. Next, we have the noisy intermediate scale quantum computers, also known as NISQ computers that use quantum logic gates. These devices have tens to hundreds of qubits, but are prone to errors. But they still provide a platform for developing and testing a greater variety of potential quantum algorithms. Finally, of course, we are aiming to the fault-tolerant quantum computers, also known as FTQC, which use error correction to operate library on a larger number of qubits. However, full tolerance, we know we have still a lot of challenge to attain this objective. So today, in a nutshell, today quantum computers are sensitive to their environment and prone to error due to the quantum decoherence. But despite this, developing software now is vital for a few reasons. First, it allows us to understand and explore the potential and the limitation of quantum hardware and quantum algorithm. Secondly, it helps to create a foundation of quantum software, tools, libraries, so that when quantum hardware does advance, we will be ready to leverage as quick as possible. Thirdly, of course, starting on quantum software now also prepare the next generation of quantum scientists, of data scientists, of engineers. By developing software now, we will streamline the learning process and also foster the innovation around quantum algorithm. It's a strategic investment. I engage everyone to go and look at this specific investment, ensuring that we are ready to leverage quantum hardware as soon as they are ready for real-life application. I can't help talking about quantum-inspired solutions, such as tensor network, which is one of our specialty, because it can be used on classical computers to solve complex problems more efficiently than traditional methods. They are being applied in optimization, in machine learning, and are already bringing benefit today, and as we showed in other CASIP project.
Thank you, Michel. Does the world of finance have many use cases that can be applied? And how did you choose the first use cases to deal with together? And how did you start this collaboration? Maybe Ali?
Yes, Fanny. Actually, the ambition in finance for quantum computing is very large. But in our case, we worked in a pragmatic way. As sponsor of the quantum initiative within Crédit Agricole CIB, I wanted to deliver value to our executive committee very fast. So this is, I think, for a company like us, very important. We do more development than research. So in order to keep the attention of our managers, senior managers, we should demonstrate the value. We should also explain how it works. So two things, the choice of the use cases are very important. The timeliness of delivery, the time to market is very important. And actually a third part is that the team that is in charge within the bank or within any company like ours of such a topic should understand by itself how it works and not work with partners in a classic a client-supplier mode. So this is how we structured our collaboration with Pascal and Multiverse. First, we were very clear about the way we wanted to work with them during the 18 months of collaboration. We wanted to co-create rather than just give them the use cases and receive the results. That's the first very important point for us. Second one is the choice of the topics. As I said, we wanted to have results with the technology at its current stage. So we discussed a lot with Pascal and Multiverse about the choice of the topics. So we knew that in the case of Pascal, the analog version of Pascal quantum computer was quite ready to be used for subjects or problems like optimization problems, and it was great because we had actually a very good candidate use case to test, and it was if I go into a bit into details, we have within Crédit Agricole CIB an algorithm that helps us predict the evolution of the credit quality of our counterparts, of our clients, so that we can manage in advance the risk position we take on our clients, either by hedging this risk or by selling part of this risk, etc., in the capital market before this evolution is priced in the market. So this is something we already know how to do with classical computers. It's breakdown into a couple of pieces, and the most important piece of the algorithm is an optimization one. We have a cost function that we have to optimize with many variables, and this is what we focus in the project with Pascal, in order to see first if we can replicate this calculation, first thing, because we start from zero, so we didn't have the pretension to achieve the quantum supremacy from the beginning. So we wanted to do it step by step. And first thing is to replicate what we know to do, a hard problem that we know how to solve with classical computer in a quantum computer. Okay, in this case, the Pascal quantum computer. And we achieved this objective after, it wasn't simple actually, after months and months of try and learn. And basically, if I had to explain what we did, that we casted the cost function into the Hamiltonian used within the Pascal computer, and which is the energy function. So with the technology of Pascal and the fact that we can use the atoms as we want, distribute them in the space as we want, and initialize them in the state we want with the integration, etc. Entanglement. Sorry, we achieved a very good accuracy in replicating the cost function, our cost function, financial cost function, into the energy function of the quantum computer of Pascal, and then just let the quantum system converge into the minimum energy state to read the result of our optimization problem. That was really fascinating, but we demonstrated that we are able to do it on a real financial problem. And I think it's a small step, but for us it's with a big takeaway.
Okay, Georges, I think you want to talk.
Thank you very much for your trust, Ali, and it's a real pleasure to hear you talking about our technologies and Hamiltonian. I think we definitely achieved something. I remember when we were discussing the result of the work we did together. I was pretty excited about them, and I will explain why later on. But the first thing you told me, George, calm down. The first thing I want is my team to understand what you are doing. And I think this is key, and this is key for all the corporates in the room here, to understand how a quantum computer works, what it is good for, and start training your team. Because in 2 years, there will be the first quantum computer showcasing a quantum advantage, and developing solutions takes time. This is what we learn. So you'd better start now, otherwise you will just work behind of schedule. So why am I so excited by this result? Because as you mentioned, it's not the first use case in finance. In fact, in the literature, you could find tons of them implemented of quantum processor. Here we brought something new, is that we implemented the use case in its full complexity. What I mean is that we solve the problem with the exact number of parameters. I don't remember the numbers, but it's thousands of them. And if you have a look at what the other did in the past, is solving a real-world problem, but instead of solving it with thousands of parameters, they did that with a couple of them. So, okay, it works, but it brings absolutely nothing to the end users. And here, for the first time, it was the full problem in its full complexity. And as a result, we were able to benchmark against the classical state of the art. And as Ali mentioned, it's the first step. I mean, before beating classical technology, you start by matching them. And we achieved that. And for the first time, and I think it's a very, it's a significant step, showing that now the technology is ready, and now is the time to start working and developing use cases.
Okay, just in 30 seconds, because we're running out of time. It's really interesting. What is the next step?
Okay, there are many next steps actually.
It's the first one.
I think the most straightforward one is to accompany the development of Pascal computer in order to test the results we can achieve with a more sophisticated quantum computer from Pascal. By the way, we used also a very important step with Multiverse to cast this function, this cost function, into the quantum computer of Pascal, which was a very important step. Otherwise, we couldn't achieve our results. This is the first one. Second one is to start to tackle problems that we now don't know how to solve accurately with classical computers. So this is now that we know how the quantum computers work and we have some assurance in using this technology, start tackling new problems like Monte Carlo simulations. This is something we use a lot in finance. So I would be very, very happy if we can achieve also some progress in this field as well. And Pascal and Georges would excuse me to say that, but we will also try to explore new technologies, other technologies like Candela, for example. It's very important for us to also help develop the ecosystem within France, and we are very gifted to have all this ecosystem around us, which is a top-class ecosystem in the world. So this is very important.
Thank you very much, gentlemen. So it's time to close this panel. Sorry, Michel, I know that you have so much things to talk.